This is my Lab 5 magnetic braking with Faraday's Law. An overview of our presentation is we'll first have an introduction to introduce the lab purpose and goals, as well as our fundamental principles used and our lab procedure. We'll then go into our experimental data collected, as well as observation and checkpoint questions answered, and then we'll go into our computational data made in our GlowScript code and show our computational model, and then we'll wrap up with results and discussion of these results. So to get introduced into the lab, the goal of our lab is to explore the interaction between the falling magnet through a conductive tube of aluminum foil. We also want to compare our experimental model with our GlowScript computational model, and overall we want to just learn and observe Faraday's Law. So the purpose here is just to observe and model Faraday's Law acting on a falling magnet through a conductive tube of aluminum foil. Our system for the purposes of these experiment will be a falling magnet, and the surroundings will be everything else. Just as a brief overview of our results, we will see that resistivity and holes will affect the falling speed of the magnet, and that there are times for our computational model in our experimental model will be pretty the same, with our computational model being 1.879 seconds and the experimental model being 1.876 seconds. Our fundamental principles for this lab will involve Faraday's Law, Ohm's Law, Newton's second law, the Beertz-Savart law, magnetic dipoles, and magnetic force. The experiment of a magnet falling through a conductive tube involves the interplay of several physics principles. And so for Faraday's and Lenz's law, our change-out magnetic field will induce an induced current in the conductor, and the Lenz law dictates that these currents produce a magnetic field which will oppose the motion of the magnet. With Ohm's law, the resistance of our conductor will influence the strength of our induced current, and with Newton's second law, the forces acting on the falling magnet, including gravity and opposing electromagnetic damping force, will affect its acceleration. The Beertz-Savart law, the magnetic dipole, and the magnetic force formulas will be used to find the magnetic force as well as the magnetic dipole values. So for our lab procedure, we first are going to mark the north pole of our magnet. We're going to use the magnet meter on our app to determine the direction of true north. Then we're going to hold our tube of aluminum foil vertically and then measure the length of our tube. We're going to then position our tube in the frame of the photo camera and then drop our magnet through the length of the tube and record with our phone. And then we're going to repeat this 5 times. So our average time over 5 trials was 1.876 seconds, and this was found after scrubbing the video. So for our experimental data, we have our aluminum foil of width 0.28 meters, or length 0.28 meters, our width 0.022 meters, which makes our inner radius 0.016 meters, and our outer radius 0.038 meters, and that is our resistivity that we calculated. Our bar magnet has a mass of 0.016 kilograms, and our mu found from lab 3 is 1.12. So for checkpoint questions, why can't we use a ferrous tube? The ferrous tube cannot be induced, so the results will not be the same. And what is happening to the magnet, and how does it compare to a magnet falling in free space? The magnetic falling in the tube of aluminum foil basically induces an eddy current or induced current because of Faraday's law. These currents create their own fields to oppose the motion of the magnet, causing the magnet to fall more slowly than if it was falling in free space. So this interaction between induced currents and their fields create a resistive force, which acts against the force of gravity, known as magnetic braking. So here's our GlowScript code. You can just see our initial conditions for the bar magnet and our aluminum tube and any other constants there. And then we have our 2 formulas calculating our magnetic field of a bar magnet and magnetic flux. And then here is our code to show the simulation loop. Here's it continued. And then this gives us this computational model, and we can see that our time in the tube was 1.879 seconds. So to interpret our simulation, the color of the tube basically indicates the current, with the color being the direction of the current. So this image right here on the right was also taken from our GlowScript code. So blue is the clockwise rotation of the current, and red is a counterclockwise rotation of the current, and the blue current is on top of the red. And Lenz's law states that the magnetic field from an induced current opposes a change in flux. So if we flip the magnet, it would actually not change anything. So our computational model could be made better by increasing the number of rings that were used to model the tube, but there's not much variation in my model. As seen in the graph, at one point, one force is greater than the other, force for about a full second, and you can see them balance each other out on the graph. Our times for our physical model and computational model were approximately the same. You can see the values here. And as we could see in that graph earlier, the shape of the velocity versus time graph tells us that there are just multiple forces on the magnet, and we know those to be the force of gravity, as well as the opposing force generated by the induced current. some potential sources of error or measurement errors, or phone not recording at the wrong time, or other magnetic fields existing. So to answer our what if questions, if there was less resistivity, the induced currents would become more substantial, creating greater opposing force, increasing the braking effect. If there are holes or slots cut into the tube, the presence of them would disrupt the closed loop that's necessary for induced current. And then our opposing magnetic field would be weaker, so it would fall more freely in these sections of the tube. Thank you.